Hi, everyone. Sorry for being blurry. Welcome back to, just 1 second, I guess. There we go. So welcome to the online causal inference seminar. We're happy to be back for this fall. And our first speaker to open up this season of seminars is Andrew Gelman from Columbia University, who will be giving a talk on better than difference in differences. So also this year, we're trying out a little bit of a different setup. So we'll have Andrew give his talk, which will be around 45 minutes. And after that, we will have kind of a free open discussion with several discussants. So this will not be accompanied by slides. So the goal is to have like a lively discussion between several people. And today our discussants are Elizabeth Tipton from Northwestern, Avi Feller from UC Berkeley, Jonathan Roth from Brown, and Pedro Sant'Anna from Emory. So hopefully you all enjoy, and please still feel free to submit your questions. I'll switch it over to Ying, who is our moderator too today.
Thank you, Emma. Yeah, welcome back. So just as usual, please submit your question in the Q&A section. So if you haven't used it before, it is a button at the bottom of the Zoom window. And please do submit the questions through the Q&A so that we can better track it. And if you have questions, please immediately submit it, because sometimes people wait for the pause to submit the questions, which is not that efficient. And we'll try to raise it if that's a clarification question. But for others, we'll wait for Andrew to stop and raise it to the speaker. So that's basically it. With that, Andrew, please feel free to get started.
Well, it's fun that you're doing this new version where we have the discussions. I always like that. I guess you're going to evaluate the effectiveness new approach using a before-after study with n equals 1. So I think that's a good reminder to us that when there are all sorts of things about causal inference that we scream about when other people do it, but then when we're trying to do causal inference, we're happy with that. I have this idea actually that the before-after study is the right an important paradigm for causal inference. So right now we have our paradigm for causal inference in most of the textbooks, including our own, is the controlled comparison, the between person comparison. Some people get the treated, or in our case, some animals get the treated, some animals get the control, and then you compare the two, and that under certain conditions that can give you a kosher causal estimate of the average treatment effect. Now there's another paradigm, which is the before-after study, where some animals first get the control and then they get the treatment, or some first get the treatment and then get the control, and you compare. That doing before-after study has problems because sometimes things might change even if you didn't do the treatment, so we're always warning against that. Basically, to make the before-after study makes the naive causal inference from a before-after study makes the implicit assumption that had the control been done, there would have been no change. And that's kind of a ridiculous assumption, so we know not to just do before-after comparisons. On the other hand, taking a standard randomized trial and using it to make statements about individual treatment effects also requires a huge assumption. And that's the huge assumption that the treatment effect doesn't vary, that the average treatment effect is relevant for the individual. If you're interested in estimating average treatment effects, that's fine. So sometimes in economics, I think we really care about average effects. And we don't care about who's buying more of the product. We just want to know the average sales. Or in public health, we don't necessarily care who's getting better, who's getting sicker, if we can reduce the average hospital load, whatever. Most of the time, though, I think in causal inference, we're interested in individual effects. And I think that before-after studies require a huge assumption, so do between-person studies. And I think they're kind of equal paradigms in the sense that they're capturing kind of there's kind of 4 quadrants, and each of them is jumping you from one quadrant to the other, but not going all the way across. So the best studies, I think, are going to be multi-level analyses where we have within-person comparisons amid a controlled, we have treatment and control, but we also have measurements before and after within people. That's not what I'm going to talk about today, though. If I did, that's probably what I maybe should have talked about today, because I think that's really I think it's really important. It's sort of conceptual, though. I probably have to get some actual results, and then I could give you another talk in a few years. So today I'm going to talk about something I have more results on, which it's originally didn't really come out as an econometrics type of project, but I started thinking more about that after I was done. So I'll tell you the story, but before I tell you the story of the chickens, I want to tell you a different story for a second, and you'll see why. There's something, okay, it came up in a consulting project years and years ago. Someone was doing lab experiment, and they had 4 treatments. They were like things that they were doing to little cell cultures in dishes, okay? So they had 4 treatments. Each treatment, you could still see me, right? Is that correct? Yeah, okay. Each treatment was done on 5 dishes, and each dish had 6 cultures in it. And they're comparing the 4. So what we're going to look at is what you do for each of the 4 treatments. And there were 2 things you could do. So each treatment, remember, it's done in 5 dishes, and each dish has 6 cultures. So you could just take the average of the 30 numbers. That's estimate 1. Or you can take estimate 2, which is you first take the average within each dish, and then you take the average of those 5 averages. Now, a little bit of math will tell you that estimates 1 and estimates 2 are the same thing, but they have different standard errors. Right? Because in estimate 1, you take the standard error by doing the standard deviation of the numbers and dividing by square root of 30. In estimate 2, you take the standard deviation of the 5 numbers and divide by square root of 5. So here's the story that the person came to us in the consulting room and said they wanted to do estimate 1 because they felt that the measurements within the 30 dishes, they felt that the 30 measurements for each treatment were essentially independent. So yes, there are multiple cultures in a dish, but they didn't really think there was any interaction going on, no dish effects, no interactions. They just wanted to do estimate 1. But they knew that you're kind of supposed to do estimate 2, because what if there's dish effects? What if there's interactions within dish? The unit of the analysis really should be the dish, not the individual culture. So they wanted to do number 2. So we had this discussion with the students, which should you do, number 1 or number 2? So number 1, you're dividing by square root of 30 instead of the square root of 5, which is like really great. Like it seems like you want to do that. On the other hand, it seems like method 2 is more conservative. On the other hand, method 2 is more conservative, but the guy told us that he didn't think there were any dish effects or any interactions with the dishes, so maybe we should respect that and do estimate 1. Sort of like going back and forth on this, and ask the class what to do. People are kind of split on what to do. It's kind of difficult problem in some way. How much should you believe in? In this case, there is an answer to this, which I'll get back to. But I want to now tell you the story of the chickens. Back in the 1980s, there was a concern that low frequency electromagnetic fields were causing leukemia among children. And this happened because there were some cancer clusters. There were kids who were dying of leukemia and they lived near power lines. Then there were some epidemiological studies, and they found a risk ratio in the 1.5 to 2 range. It was a puzzle, though, because if power lines are causing leukemia, how does it work? So the energy, 60 hertz power line, had the photons have too low energy to ionize your cells. It's not like being exposed to X-rays or gamma rays. They're even lower energy than microwaves, so they can't even cook you. They can't even do that. So how do they do that? So some biologists had remembered something, which is brain signals are roughly at 60 hertz. And so the hypothesis was that the magnetic fields were interfering with your brain waves and not causing cancers to initiate, but inhibiting your body's ability to fight cancer. And why childhood leukemia and not other things? Well, that's actually pretty clear from an epidemiological standpoint, that there aren't that many, that cancer rates are very low among children, and so it would be more noticeable. And among adults, even if you have such a small effect, it just would be swamped by all the people getting cancer from other sources. So based on this theory, in the 1980s, some biologists did a series of experiments on chickens. They took a bunch of chickens, they kill a chicken, take half the brain and put it in one, and they take out half the brain and they measure the calcium efflux, the flow of calcium from the chicken brain. And then the other half, and that would be in a room where there was a low frequency electromagnetic field. They take the other half of the chicken brain and put it in a room without without the electromagnetic field, and they compare the calcium efflux. Calcium channels are involved in brain signaling. That's all I know about that. So I got no more biology for you. Okay. And here's some data. They did a series of 38 experiments. They did 1 hertz, then 15, 30, 45, 60, all the way up to 510 hertz. And in each frequency, they took 32 or 36 chickens. They were in batches of 4. So there's actually some clustering in the data. I'm not going to talk about the clustering in the data because I don't have the raw data. All I have is the estimate and the standard error. And also one more thing. At each frequency, they did a sham experiment. So they did 2 experiments in each. So let's just take the first row, okay? At 1 hertz, they had 32 chickens in the sham. So what they had was 32 chickens divided into 2 halves. I mean, they didn't do it all at once, but in a sequence of measures. They measured the calcium efflux in the treated group minus the calcium efflux in the control group. And it's normalized, dividing by the average. So an effect of 0 would be no effect, but it's relative to the average level. And they get an estimate of minus 0.405. That's the average with a standard error of 0.041. All they gave me is this, so I'm going to have to take their word for them that this standard error accounts for the clustering correctly. Then they did the same thing with real exposure. So the point here is that they want the real exposure. The last column is what we really care about here, is in the slide, is the real exposure. But they did this sham treatment too, just in case, because what if there were some defect of their design and they're introducing a bias? So what they did is at each frequency, they took the real exposure, the estimate from the real minus the estimate from the sham, and then they took the standard error of the difference, the square root of the first standard error squared plus the second standard error squared, got the uncertainty estimate. And they did that for all 60. They did that for all 38 experiments and reported their results. And look at the top row is what they reported. I redrew their figures in R, but like this is basically what they showed. At each frequency, they displayed the estimate as a bar. You notice almost all the estimates are positive, but 1 or 2 are negative. Just it can happen that the effect seems to be negative. So positive means, I guess, more calcium efflux, that the magnetic field had an effect. The black bars are statistically significant. They're at least 2 standard errors away from 0. And you see a pattern here. They discussed this. They also plotted the p-values. So at the top are things that aren't statistically significant, and at the bottom you have things that are moderately significant and highly significant. And in their report, they discussed this. They distinguished I drew these dotted lines, or maybe they distinguished frequencies. If you notice, it's alternating. So it's like every 30 hertz, there seems to be something going on for most of the time. These are large effects, highly statistically significant. Then there are some others that are moderately significant, and then others that are not at all. So I read this paper. I mean, my personal background is I happened to go to a conference, and was on this topic, and people kept referring to this work. And so I went to the library and looked it up and made some graphs and replotted things. I was concerned about the use of the sham. So if you go back, if you look at this, you notice the exposure, the standard errors are about 0.03, 0.04. If you look at this, you'll see that some of these effects are much larger than 2 standard errors away from 0. I mean, and there's no like p hacking or whatever. This is the data. Like there's evidence that something's going on. Some of them could be 0, but some aren't. The sham, though, if you look at them, there seems to be nothing going on in this sham. When you think about it, that actually makes sense, because these are chickens, right? I mean, this is an experiment done on chickens, so it's not like a sham. Like, there's no reason why there'd be a placebo effect. They're dead chickens, actually. I mean, like, there's really hard to see. It's not that that the sham treatment couldn't do something, but there's no evidence that it does. By subtracting the sham, you're actually multiplying your standard deviation by square root of 2. You're essentially halving your sample size. So I thought maybe they should do better with that. So if you look, I can look just at the exposed data, and you get actually more things that are statistically significant. You get smaller standard errors. Here, I jumped ahead there. I felt like this is probably these estimates are probably better, because they're less noisy. I looked into it a little bit. These are the estimates. These are the 38 experiments. This is just the sham. If you actually look at this, there's no evidence. This is the estimate plus or minus 1 standard error. And if you look at it, there's no evidence. Like, this is completely consistent with it being 0 throughout. I also thought there could be a more subtle signal. So I plotted the estimate from the sham data versus the estimate from exposed data, and I see nothing there either. So, okay, this was 30 years ago. So this is where we stood, which was they lost a factor of 4 in efficiency in this experiment. Okay, they lost a factor of 2 in efficiency because they're subtracting the sham. They lost another factor of 2 in efficiency because they collected the damn sham data in the first place. So they wasted half of their data collection effort as well as half of their analytic work, which is, we see this a lot in statistics, that you get about half your efficiency from the design and about half from the analysis. But this was gnawing at me for decades. And the thing that bothered me was, it's very clear what to do here. Like, you shouldn't use the sham, but that's because there's no evidence of any sham effect. And what if there was evidence of a sham effect? Then I would have to subtract the sham, but then, like, I subtracted, I'm doubling my standard errors. Like, do I double my standard error or not? It was a little like that earlier question. That's why I brought up the earlier thing with the cell cultures. It's like, it's an awkward decision. So then it bothered me, because when I do Bayesian statistics, I get to compromise, right? It doesn't seem right to either throw away the sham data or subtract the sham data. There must be something in between. And it bugged me for the longest time. And then suddenly it became clear to me what to do. And so I wanted to share that with you. So here's a model. Yes.
Can I just ask a clarifying question that I and a couple of the other panelists, I think, were slightly unclear on? I'm probably just too chicken brained to understand the experiment here, but so can you explain just exactly how the sham works? So is the sham, it's the same brains from the other half of the same brains from the chicken? Okay.
Yeah, different brains. Okay. There's 2 experiments done at each frequency, a real experiment and a sham experiment. The real experiment, they have 32 chickens, they're divided in half, and half of you see the ends are different in row 2, so you can see they can't be the same chickens. In this real experiment, you get, I guess that should have been the first column, that would have been more clear. In the real experiment, you brought up 32 or 36 chickens, half of them get the treatment, half get the control. The treatment is exposure to this electromagnetic fields while they're, the chicken brains are sitting there leaking calcium, okay? The sham, we do another set of chickens. It's the exact same experiment, except in the room where they did I don't literally know if it was the same room. Let's say it was. In the room where they were doing the treatment, they unplugged the machine. So it's like the sham. It would be like, it's like they're pretending to do it, but they're not actually doing it. So you could imagine reasons why there's sham effects having to do with experimenter effects. You could imagine something to do with where the room is and a truck rattling down the street. Like there's lots of stories you could imagine. In the data, no evidence of any sham effect, which is no surprise. You wouldn't expect to do it, right? You wouldn't expect to see something. Okay. So here's the model. Interrupt again if there's something unclear. So I'm going to model the data. Now, again, I have the luxury of not having raw data here. I mean, I'd rather model the raw data. So yj1 and yj0, J indexes the experiment. And I'm modeling the exposed estimate and the sham estimate. And what it's a randomized experiment. So the exposed and the sham are unbiased estimates of something. Of what? Okay. So the idea is that theta j is the true effect. That's the effect of electromagnetic fields. Bj is the bias of experiment j. So experiment j has its own bias. And then the sham only measures the bias. Now, you might say, why do I have a separate bias for each frequency? Why should that be? Well, the answer is I'm respecting the design. So in the design, they had a separate sham experiment at each frequency. So that implies that they thought there could be a separate bias at each frequency. So if you take, don't even look at the priors yet, just take the first two rows. I'm also assuming statistical independence of the measurements. They're different chickens, etc. So it's very obvious what to do. I mean, this is wrong, but very obvious, which is you take the second row and you subtract it from the first row. Yj1 minus yj0 is normal with mean theta j and standard deviation square root of sj1 squared plus square root of plus sj2, sj0 squared. That's it. So the difference in difference estimate, right? Yj is already a difference, right? Yj1 is a difference, yj0 is a difference. The difference in difference estimate is unbiased, and it seems obvious that's the right thing to do because math. Right? You subtract them and the BJ drops out and it looks right, but it's not the right thing to do, actually. So we can do the right thing. We can do a Bayesian analysis. Well, Bayesian analysis is the right thing conditional on the model being correct. So what I'm saying is that the difference in difference thing is not the right thing conditional on the model being correct. But that's already something. It looks so obvious, but it's wrong. So I'm going to put priors.
So Andy,
yes.
well, let me just interrupt you here very quickly. So the notion of differences and differences here, it is slightly different than the notion of difference and differences like in the literature, because you're not exploring time, right? So he is more exploring, you have two populations or two subgroups, and you're doing like, there's no before and after. Is that the case?
Yeah, it's well, difference and difference is not always using time. It's not always before and after, actually. But yeah, it's mathematically a difference in differences. It's mathematically the same, but it's a different substantive context. And I'll get to that at the end. I mean, if I want to jump to my last line of the talk, my last line of the talk is that this is mathematically the same as difference in differences, but it's a different substantive context. And I'm very interested, I don't have the answer to this, I'm interested in how this applies to those substantive contexts. And my belief is that we can apply the same model to difference in differences over time, because I think the math is the same. But you're right, it's literally a difference in differences, but it's not the variables that we usually use in that way. So thanks for pointing that out, or jumping to the end, or whatever. Okay. But the point is the math is the same in that it seems very appealing to subtract those two things. Now, but I can do a Bayesian analysis and put priors on the biases and on the effects. I can actually have the priors be correlated. I can have it could be that when there's a large effect, there's a large bias. This particular setup, I didn't think that was going to make sense based on the context. There's no reason why frequencies with larger effects would have larger or smaller biases. So I modeled them as independent. Everything's going to depend on these priors. Fortunately, we have 38 experiments, so we can estimate the hyperparameters. So the short story is when we fit this model to our chickens data, you estimate mu b to be essentially 0, and you estimate sigma b to be essentially 0, meaning that you estimate there to be no biases. And so then that means that the BJs are going to be very small, which means you end up basically using estimate based on exposed only, and I can show you the results. So on the left is what I got, and on the right is from their original paper. Now, I want to look at this for a second. I mean, some of it's kind of obvious, like they have some really high estimates, and given the spread in the data, it makes sense to think that those are going to be overestimates. If you look at this, you might say, well, they look kind of similar, and they do look kind of similar, but they actually have different scientific implications. So so here's a quote from the original paper. They looked at one set composed of two groups of 30 hertz, the response at 60, 90, and 180 hertz, an elevated but not statistically reliable response at 30 hertz. These are all things you can see kind of. The response at 405 hertz might represent another set. There is a article in the New Yorker that was published about this stuff in the 1980s. It was like a scaremongering article. It said that they were trying to find out why fields with frequencies of 15, 45, 75, and 105 hertz should have such a strong effect on calcium ion outflow from chick brain tissues, why fields of 30, 60, and 90 hertz produced only a weak effect. Now, what I want to get to you is that you could kind of see that in the original claim from the exposed data and the original p-values, but when you look at the estimates from the hierarchical model, you don't see that. We don't see zero variation. We see effects of something going on, but the scientific conclusion has changed. And so I think this is important, that not only are we getting more statistical efficiency, but we're actually changing what's learned about this. So then there's a couple other things I want to share before getting back to kind of these larger questions here. One question was how to evaluate these approaches. So we ran a set of simulation studies. We actually ran two simulation studies, one from the model and one where we bootstrapped the data and added effects. But I'll just talk about one of them because they gave similar results. So what we did is we simulated from the model, and the x-axis on these are four different outcomes. The x-axis on the graph represents how important the sham is. So all our simulations, we assumed a zero mean sham effect, but then we allowed the scale of the sham effect is the standard deviation of the sham effects across different experiments. At one extreme, the scale of the sham effects could be 0, which is kind of what we observe, that the sham looks like pure noise. On the other extreme, the sham effects could be as high as 0.1. Now, I used 0.1 as the highest of the variation of the sham effects because if you look at the actual data, typical effects in the data were about 0.1. So it seems like if we're doing a simulation, it would be silly to do a simulation where the sham effects are actually larger than the effect sizes we might care about. So this 0 means basically don't worry about the sham. A 0.1 means the sham effects are as large as the treatment effects themselves. That's how important it is. We considered 3 estimates. We considered the difference estimate, which is what they did in their paper, the exposed only estimate, which is the kind of simple thing, which is don't use the sham at all, and then the Bayes estimate, which adjusts for the sham, partially adjusts. And we looked at, there are 38 experiments. The first outcome we looked at was how many statistically significant estimates there were. Now you might say, why am I looking at statistical significance? I hate statistical significance. And my answer is, I'm trying to respect the researchers and their research flow. So just as in their design, I'm allowing the sham effect to vary because that's their experiment. Similarly, I know that they're going to use statistical significance in their summaries. So my question is not, do you have a lower mean squared error? Well, I looked at that just for laughs. Unsurprisingly, the Bayesian one wins on mean squared error because it's designed to do that. I also wanted to look at outcomes. I wanted to look at how this would affect their outcomes. So the first thing is, if you do exposed only or Bayes, you get a lot more statistically significant results, which makes sense because you're reducing the error. Both doing the exposed only is a way of reducing your uncertainty. Now, the Bayesian, as the scale of sham effects gets larger, you're getting more statistically. This is a somewhat of an artifact of the fact that the mean estimate is not zero. And so the Bayes partially pulls toward the population mean, doesn't partially pull towards zero. So then you're getting more statistically significant estimates. The type S error rate is the probability that a statistically significant estimate is in the wrong direction. So what happens is, well, the difference has a higher type S error rate at low sham effects because it's adding noise. As the sham becomes more important, the exposed only estimate becomes horrible. Look at this, because I'm ignoring the bias. So I'm not correcting for the bias. So the exposed only estimate has narrow standard errors, but it's wrong. And you see that in the type S error rate, because the type S error rate just goes up and up and up. Because you're not doing correction. If you correct for the bias, you control your type S error rate, which makes sense. You can look at root mean squared error. Again, exposed only gets worse as the scale becomes larger. The difference is bad when the scale of the sham effects is smaller. Finally, because it's a simulation, we can look at the rank correlation of the estimates with truth. And when the sham effect is zero, the Bayes or the exposed only gets the right ranking of the effect sizes. Well, 0.8 correlation with the truth. When the sham effects are large, the difference the Bayes is pretty much the same as the difference in terms of the ranking. And you might argue the ranking is what you care about the most. So the Bayesian analysis, it's no surprise, it's an adaptive method. It partially pools. So when there's evidence of no sham effects, it shows you it does what you would do if you were going to have no sham effects. When there's evidence of large sham effects, it's going to give you something similar to taking the difference. So that's what I was looking for, and I found it, and it made me very happy. But then it just made me think of the whole world out there of researchers, right? Because here you've got people doing stuff like this all the time. It seems very natural. Well, this is very common, right? We have an experiment where we have noisy controls and we need to adjust for the noisy controls. And then I thought, well, this is a form of difference in differences. And it has this seductive thing where you can subtract equations 1 and 2, 1 and 0, and it looks like the difference of difference pops out. But in this case, that was giving the wrong answer. So I thought the adaptive thing was very important. Now, there's a few other things we did in the paper. You can, if conditional on the hyperparameters, you can frame the Bayesian estimate as taking the exposed minus beta times sham, where beta is some number between 0 and 1. So the relative values of SJ1 and SJ0 map to a beta between 0 and 1. Beta not being this B, but beta being like your lambda, how much you're subtracting. It's a little more complicated because also you'd also be subtracting the mean of the sham, but you can map that and you can get a kind of equivalent linear estimate, which I thought could be useful for people for explaining. So the right thing to do, we have an experiment, we have noisy controls, we do the Bayesian analysis, here it is. This is equivalent to subtracting, taking the exposed minus 0.6 times the sham, right? That's how much. Okay. It's like in education research, people would look at gain scores. They'd look at they'd look at post minus pre. They'd look at after minus before. But the right thing to do is not look at after minus before. The right thing to do is run a regression and look at after minus beta times before, where beta is a number which is typically between 0 and 1, which is the coefficient for the pretest. The only difference is here, you don't literally run a regression because instead you fit the hierarchical model. Let's see, I did some robust studies, which I'm not going to show you. I wanted to comment to loop back here the practical import of this. people often feel bad about not doing an unbiased estimate. So in the paper, they wrote that they optimized their procedures. They're clearly under cost constraints. They wanted to follow up. This paper is cited hundreds of times, but they never got around to following it up. So if they had done an experiment and just thrown away the sham, it would have been as if they had done an experiment that was twice as big. It would have been as if they had 64 chickens in every experiment for free. If they had not even done the sham experiment, it would have been like having 128, or they could have done more frequencies. They could have replicated for free, a factor of 4 that they threw away. And that factor of 4 had real impact in this field. It's not like, oh, like, I'm a tough guy. I care about unbiased estimates, other people care about precision, but I'm a fundamentalist. For me, it's all about bias because I'm doing science. No, these people are doing science too. Unfortunately, they threw away 3/4 of their data, so they couldn't do as much science as they wanted to do. Okay. If you can afford to throw away 3/4 of your data, great. Okay. But people can't always do that. And I really tried to loop that back into the claim. Now, 3/4 is a little overstating because presumably the right thing to do would be some sort of adaptive design, like gather some sham data, and then you see it has no effect, and then you can go on from there. You can partially adjust, you can gather a little sham data. That's fine. Like it makes sense to do that. Of course, in economics and political science, we often have observational data. Often the before data come for free. So in that case, it's not a data collection question. Now, I wanted to, quickly go back and mention my...
Andrew, can I just interrupt for a second?
Yes.
So the sort of throwing away the lots of data makes it sound very bad. But
Yeah.
Don't you feel there was some value to doing that analysis and showing some robustness? I think in a lot of cases, there's so much experimentation going on that you do worry that sometimes the experiments are not done correctly, and having this type of analysis gives you a little bit more faith that the experimentation was done right.
I agree.
I'm not trying to defend here the particular analysis, but the idea of doing the sham analysis, I'm totally on board. Doing the sham data, I'm totally on board with. I think that's very useful.
Okay, so yeah,
often
I agree.
Experiments we do that are so complex that
actually... Okay, I agree. Okay, so let me take 2 things. First, conditional on the sham data existing, it's doing the analysis both ways is great. And then especially if you end up doing the correct analysis, and then you can say, sure, isn't this interesting? They've learned that there's no sham effect. Like, sure, that's great. And as I said, in political science and economics, we often have that control data almost for free anyway. And so that I would agree with. Arguably, they didn't know ahead of time that they didn't need to do the sham data. In retrospect, they did overkill. They did not need to do 38 sham experiments that were full size. They could have done less. But I agree. The factor of 2 in the design is a tougher call. The factor of 2 in analysis is truly free, but the factor of 2 in design is not so. Now, I wanted to get back to, remember the example from the beginning of the cell cultures and all that? So there's a funny story here. So remember, estimate 1 is the like ballsy estimate, like let's let all hang out. We get a smaller standard error. We're going to take their word for it. Estimate 2 is the conservative estimate, but you only get to divide by square root of 5. So which should you do? Now, the answer here is that you should do estimate 2, because estimate 2 is safer than estimate 1. Also, if it's actually true that the measurements within each dish are independent, then estimate 2 is basically the same as estimate 1, because yes, in estimate 2, you're taking you're taking a standard deviation dividing by square root of 5, but the standard deviation in estimate 2 is a standard deviation of means, and each one is a mean of 6. So you're really dividing by 30. So the answer is estimate 2 is better. Well, there's some benefit from doing a multi-level model, because as Guido said, like you learn more from the multi-level model. So multi-level model would be better, but actually estimate 2. So I want to tell you a funny thing. In this first example I gave you, there is an answer, and the answer is, the quick answer is do the conservative thing. There's a long answer for the multi-level model, but the quick answer is do the conservative thing. It's better. You lose very little. It's safer. Do it. In this example, the message is, well, yeah, you should do a multi-level model, blah, blah, blah. But if you have to do only one thing, it's better to just use the real and to the exposed and just discard the sham. And so I wanted to say that because these two stories, which both have a multi-level structure, have different, like the surface message of the first example was, be careful, do the conservative thing and you're fine. The surface message of the second one is the opposite. And you can see, though, how the people did it wrong, because they were under the training, like, well, there is a sham, doesn't look like anything's going on, but let's be conservative. And my point, and my meta point is, in some settings like this, conservatism loses you almost nothing, and let's be conservative. There's a lot of situations like that in statistics where we should just like fit the multi-level model, put in the measurement error model, whatever it is. There are other situations where what seems to be conservative leads to this kind of disaster. And so we can't follow simple, naive heuristics. So my conclusion is about the difference in differences, and this is like the tough part, which is that in political science and econometrics, we often do difference in differences estimation. Like some states got the treatment, some states got the control. We compare before and after. My feeling is that we should be doing something closer to what I did in this talk. I think that we may sometimes be really killing ourselves by doing difference in difference estimates. The challenge is that we don't have 38 replications of the experiment, which means that we can't just estimate the hyperparameters from data. So then that means your inference is going to depend on some prior parameters, but maybe so. But even so, I think it could be worth it if we're sometimes in situations like this. So it's kind of an open research question. Maybe the title should have been sometimes better than difference in differences. And now I'll stop at that.
Thank you so much, Andrew, for the great talk. I think we first raised some questions from the Q&A, and then we can head to exciting discussion. So the first question we have is, well, this makes sense also for adaptive experiments?
Sure. I mean, I think I didn't really get into design, but yeah, I mean, it should. I haven't done research on this, but I would think that you could do additional. You get design gains from analysis and gains from design both. I would hope.
Thank you. We get another question on, is there any method for using difference in difference on continuous treatment? And what could be their interpretation if potential outcome is continuous too?
I think I mean, the continuous treatment, you'd probably set it up as a regression model so that instead of like, I mean, really, ideally, you'd be modeling the raw data for one thing, but instead of saying normal, remember the outcome was normal theta plus B and the control was, and the sham was just B. So if you had a continuous treatment, then the outcome would be like theta J times the treatment so it would just be a regression coefficient. I don't think it would change anything. But maybe you should have the discussants, right, speak, because there's not that much time, and I don't want them to not get a chance, because otherwise it's just me keep talking.
For sure. So yeah, please, the discussants, please feel free to kick in as we talk about the questions. So the next question is about whether other Bayesian priors for biases and effects change the results and performance of the approach.
In our case, it didn't change the effect much, but that's just because if you look at our data, there was no real trend, and there was no real clustering. We fit a trend model and a Gaussian process model, but because of our data, there wasn't much there. I do think it is an issue. Like if you saw a trend, you'd want to model the trend, so it becomes more of a modeling challenge, which again is like, I think it's kind of worth it if you have that much uncertainty in your results.
Thanks. So the last question we have is about whether the whole thing can be get back again to how this maps with difference in difference, given there is no before and after. But
I think right, but to me, right, I feel like the exposed and the sham would be like the after and the before. I mean, in my mind. But again, like to me, I think the biggest challenge is that you typically don't have like 38 of the experiments. But I'm not sure. I do feel, yeah, I mean, it would definitely be good to apply this. We have two examples in our paper, and they're both like biomedical examples with multiple experiments. So they both have this structure where you're estimating a series of parameters. And I understand that often, like in social science, we're estimating only one parameter, and so it's harder. Although often we are interested in variations, so it might be possible to do that. But obviously this would be like, that's the next step is to have an actual example that's more like a difference in social science.
Great. Thank you for the discussion. Yeah, I think it's time to start discussion. Emma, do you want to say something?
Sure. So yes, so now is the time to move on to the discussion. So as Andrew said, after this talk, we will have a sample of one of this example of the setup. So now we're still at sample 0. So the idea is, I think all of you should get a chance to comment and or ask Andrew questions about the talk. So I'll just open it up and hopefully we'll have something interesting to discuss. So whoever wants to chip in first, please go ahead.
So I'm happy to start. Andy, thanks for the interesting talk. I think in economics, diff and diff is so ingrained as the default method that even raising the point that there are methods other than difference in differences, even if they're not necessarily better in all contexts, is sort of progress in terms of how empirical people think about what they should be doing in different contexts. So I think it's useful to kind of go down the chain of like, should we really be using difference in differences depending on the setting and the assumptions that we're willing to make. One question I had related to what you were talking about is so as Pedro mentioned earlier, kind of in, I would say that the usual difference in differences, at least as they get used in economics, and I think in political science, often involves some form of panel data where you observe observations of the same units multiple times, which I think kind of in your example would roughly be equivalent to if we observed like, half of the brain for the chicken under the sham experiment and then half of the brain for the same chicken under the treatment. And when you're in a setting with repeated observations, one simple alternative to difference in differences is that you run a regression where you control for the sham outcome for the same unit. Or, if you want to be a little bit fancy, a la Winston Lin, you can control for the lagged outcome interacted with treatment status. And that approach, in some sense, kind of, I think, addresses your efficiency question when you do have randomization, in the sense that if the sham is not informative, the beta on the sham outcome is going to be 0 with a reasonably large sample. And so you sort of get what you would get if you just did a difference in means. But if the beta is really important, then you get a larger beta. If the coefficient on beta is 1, then you basically get diff and diff. So under randomization, it kind of interpolates between these things in an efficient way. There's of course then the question of, well, like, maybe you had the sham for a reason because you thought that there's some bias. And if you really believe the bias was the same, then diff and diff is like the only thing that's going to be unbiased. Although there are some results that, like under conditional randomization, the ANCOVA you would run for covariate adjustment is also efficient, or also at least consistent under sort of conditional randomization given the lagged outcome. So I guess I'm just wondering, it seems like, especially in the case where you have panel data, there are sort of more traditional frequentist ways of dealing with this. Obviously, there's no problem with being Bayesian, but I guess I'm wondering kind of, especially in settings where you have this option of adjusting for lagged outcomes, how do you see sort of the pros and cons of the hierarchical model that you're proposing versus the regression, approach?
Yeah, so okay, quickly a few things. So first, yeah, I think that like one funny thing is that like even like, yeah, people have I've seen this a lot, like in medical literature too, where people have the before and the after measurement, and they literally take the difference, the gain score, and that's all they analyze. And yeah, you can regress on the pretest score, and if the regression coefficient on the pretest score is 1, you get the gain score. In other words, you get something different. So, and I saw a paper. This was a estimate of effective stenting for hearts, and they said, well, there's no effect. And well, actually the p-value was like 0.2, and they took the gain score, but it turned out that yeah, it was randomized, but just from randomness, the pretest averages were different in the two groups. And when the adjustment, instead of having a coefficient of 1, which is the gain score, you have a coefficient of 0.8, and then the p-value goes to 0.09, which, well, it's not statistically significant either, but the point is that it can change your result. So yeah, so I think in this case, you can't quite, in my example, you can't quite do that. If you can, that's fine. I think the analogy might be that even in your example with the panel thing, the best thing to do, if you think about these as being measured with error, I mean, here it's obvious it's measured with error because you're like taking average responses. It's always measured with error, right? So the right thing, the optimal thing to do would not be to include the mean pretest score as a predictor, or the mean it's not to regress on the before score. It would be to regress on the expected value of the before score. That's even more statistically efficient. Well, you don't know it, but if you knew it, that would be the right thing to do. But from a Bayesian point of view, you can regress on the expected value, and that's a measurement error model. And under certain circumstances, it reduces to just regressing on the pretest, but other cases you can get more information from that. So I think that would be in some way the right analogy. Regarding the thing being unbiased, I'll just kind of say what I said before, which is that like that's why I tried to get into these goals of like what people are really interested in. So I guess I've seen a lot of different things where people aren't regressing on this before thing, and there's got to be some unification of that.
Yeah, thanks, Andy. I'm happy to go next, right? So I was wondering if you could comment on a little bit more about, is this actually a difference in differences? Again, like doubling down my question earlier, or this is more like a setup when I have multiple comparison groups, right? I have, I don't know, in your case, you have like one comparison group coming from the experiment, 2 comparison groups coming from the sham experiment. Because since there is no leveraging of the like panel structure of this kind of like mapping units from the 2 groups, how does this differ? I mean, in terms of like conceptually.
Oh, well, maybe you're right. Like, I mean, I guess terms can be used in different ways. So here, yeah, I am thinking of it, just imagine one frequency at a time, right? So for one experiment, you have like, you're taking the difference to me, I think of it as it's literally a difference in differences, because you're taking the difference for the exposed group, and for the exposed experiment, you're taking the difference for the sham and you're subtracting them. And it has this motivation that you get the unbiased estimate of theta. So I think that, I guess what I would say is probably what you're talking about has a different covariance structure, but it has the same mean structure. And I guess I agree with your implicit point that when your data are correlated in that way, that gives you kind of statistical leverage you wouldn't otherwise have. So yeah, I'm not making a statement here about the practice of difference in differences necessarily. I will say I've seen a lot of talks and I've read a lot of papers that do difference in differences, and I think they'd be better off not subtracting the full difference. Because I do think it often adds noise. I mean, sometimes it's very like obvious, like there are situations where they don't have a lot of control cases, and so the control, by subtracting, you're just adding huge amounts of noise. But I've definitely seen that. I wouldn't say it's necessarily a problem with the best econometrics that's out there, but I do think it's a real issue with practice.
Andy, so I've been thinking about this in relation to the field of psychology, where I think there's a lot of concerns with experimenter effects. So that people often do in lab studies. They have these conditions where they're looking to make sure that just by being studied, people aren't responding in different ways. So that's a really important feature. And the other connecting point that I think that what you're talking about fits with is the sort of use of proxies. This is slightly different, that you have different outcomes. So I'm doing a math intervention study and I want to see the effect on math, but I should not see an effect on English. And so trying to get at the mechanism there where I'm looking at two different outcomes to sort of isolate a causal effect. And so I'm just thinking that I think what you're talking about is more broad, that there's a variety of these ways in which we try to get at bias. And I'm just curious, like this sort of broader framework of what I think you're saying is that when designing studies and you are worried about that bias, you don't need as much of sample in that bias group as you do in your outcome group. Is that kind of what you're saying? Or is that only true here because it happened to be a zero effect? Like if it were that the bias,
Oh, no,
bias,
it should definitely work if there's, no, it should definitely work if there's not a zero effect. I mean, I think there's a lot of contributions to this work. I mean, I'm very happy with this project that so far, because it was something that bugged me from 30 years. But like, I do think that the idea of thinking about the equivalent linear model is interesting. I think the idea of evaluating it the way we evaluate is interesting. I think the general answer is measurement error models. So until like, to me at least, before I had Stan to compute stuff, it was hard to fit measurement error models, and it was a lot of programming, or there'd be some theory, you'd have to assume certain things. It's really very easy now, and I think we haven't done enough of it. We're just say, like, I have some data, so yeah, I can regress on the true value, even though I don't observe it. I can set up a measurement error model, and I think we're not in the habit of doing that. And I mean, education research, they've been doing latent variable models forever. And so I think that's, you know, it's very, very natural to do that. So I think that's the link. But again, as we saw in our example, so much seems to depend on the details of the problem. And that's why, like, although, as I said, it looks like difference in differences, I don't, like, it would be good to have a kind of live example of difference in differences from an applied econ problem to work on. And I'd be happy if the answer was they're already doing it, or even my method is worse, or like, I'd just be happy to learn how it applies. Given that it took me 30 years to figure this one out, like, I can see that it can be a challenge. And yeah, someone had a question about synthetic controls, and I have a whole rant about synthetic controls, which is that I think I saw a really bad synthetic controls paper recently, and I always thought synthetic control would be like, I have data from like New York State and I want to compare it to the rest of the US. So I divide New York State into little counties, and then I find counties in other parts of the country that are like New York State, and I create a kind of pseudo New York State, or several of them, and compare them. And that always sounded really cool to me. Then I found out that people are doing synthetic controls by taking New York State and comparing it to a weighted average of other states. They'd find like, you know, 3 other states or some number of other states, and take a weighted average of them and look at the time trends. And I am like, that is not synthetic control. As well, apparently it is, because things are what people call themselves. But to me, this was like, you're losing the benefit of it, and you're just fooling yourself. So they created this weighted average where in the past time series, it looked like a perfect match. And then going forward, it's all crap. But there's no logic to it, because you wouldn't think, I mean, it's not terrible. I guess a weighted average of other states isn't the worst thing to do, but you're losing the fact of
there's no logic. There's no logic to it. Let's just kind of be.
Well, I'm just saying the term, that's similar to my thing. Like, I'm misusing the term difference in differences, and that's bad, you know. Well, the term synthetic control is so appealing that it gets used, and then it turns into a method that people use, and they're not ever even breaking up into subgroups. So they're losing that benefit. It's like, I mean, you might as well be doing regression discontinuity and just taking your research and throwing it straight into the trash. I mean, what's the point? Yeah.
Well, the Alberto Abadi is not here, but when the original type of applications was a setting where there were no subgroups that you could divide things up more, and I think where they were applying it was a very reasonable and very innovative way of getting more credible estimates than what people were doing before. And I think that's
methods have zones of applicability. So for sure. And I think that's one of the problems of the way we write textbooks, right? Is that like we have a regression discontinuity example in our textbook and it works really well. Then other examples and they're terrible. The method seems like the same, but actually it doesn't, that's a topic of another talk. But
yes,
but yeah, I think that it's that's a complicated thing, but I won't talk about that.
Right, Avi, yes, please go ahead.
I really don't know how to go after that last string of comments. As always, Andy, it's wonderful to have the chance to have a lively causal inference discussion with you and the other panelists here. I think a few things you said really did resonate with me. So this idea that sometimes we're better off not subtracting the first difference is often kind of folk wisdom among a lot of applied econometrics folks I know, where it's the only time we really believe a diff and diff is when one diff would have been enough. And so often people kind of take diff and diff sort of seriously, but not literally in that sense. I think that's actually a quote from Winston Lin. And so, I think really what you're saying does in fact kind of align with some parts of research practice. I think one thing I do want to push you on a little bit, recognizing that your paper did largely focus on this experimental setting rather than the panel setting, is I think a lot of us came here today anticipating a lively debate around panel inference methods. And we got there a little bit with synthetic controls. But I would maybe push you a little bit on this idea that actually adapting the kind of Bayesian hierarchical models to the panel data setting can be a little bit non-trivial. Like I've written some papers on this, lots of other folks have written papers on this. So it is a sort of fairly well-established literature. But I think, for example, your idea of saying in this kind of chickens example that you have, you view the sham versus the real as the kind of before and after, and that imposes a particular hierarchical structure. But you could, for example, view it the other way and and put the hierarchy the other direction, or imagine something that has a kind of a joint hierarchy. And these decisions, there start to be more and more of these decisions, particularly as you add more and more time periods, right? I think adding structure on this problem is turns out to be non-trivial. So I'm kind of curious if you've thought about that and how you might.
I think, okay, so two things. First, to get to your first point, it's very interesting what you're saying, that like you do the sham to find out that you didn't need to do the sham, which is related to Guido's point. Like they didn't really waste half of their experimental effort because at least some of that was valuable in validating it. It's kind of funny, they had the worst of both worlds because they went to the trouble of using half of their data gathering effort on the sham. Then they successfully could find that the sham didn't matter, and then they still used it to double their uncertainties, or multiply their standard errors by square root of 2. So that was kind of a worst of both worlds. But you're kind of right. It's an interesting point that if the sham had mattered, would they have written the same paper? Like, would they have said, like, well, we're concerned, we better understand what these biases coming from? Like, would I be happy? Like, I made those pretty graphs showing how great the estimate performs under all conditions. But if the sham effect had really been as high or comparable to as high as the treatment effects, would I have just said, like, glibly, like, yeah, let's do the Bayesian analysis. We've corrected for the bias. Like, what's your problem, right? No, I'd probably be like, what kind of experiment is this where the biases are larger than the main effects? Like, this is ridiculous, right? So you're right. I hadn't thought about that at all. It's interesting because it makes the original researchers look worse in some ways as data analysts, but it's an interesting point, and it is like the Bayesian approach kind of doesn't always capture that, because we're conditional on the model, you can do anything. And I mean, there's some implication about robustness. I've seen a lot of differences where I think where people just do the difference and don't think about that issue. I think it relates a lot to my very initial comment about before after studies as being a paradigm, that when the before after study isn't good and you do need to do this controlled experiment, then why do you need to do this controlled experiment? Like, that's related to the idea of like, what is a placebo effect and things like that. So I think there's actually that little comment of yours, Avi, I think is actually a super important point that I hadn't thought about before. Regarding your other question or comment regarding the model, my only thought, I've had this thought for a long time, but I haven't done it, is that when we're controlling for the pretest or regressing on the pretest, I feel like, and you made the point I thought about too, actually, how you could flip it around and do it in either direction. Like, how do you think about that? Is that the symmetry, like, because substantively pretest post-test is not the same as treatment and control, but you're taking the difference either way, and yet they have a different feel. So I felt that the way to make the math respect the science here is to say that you have a time series. Like, even a pretest post-test is a time series of length too, but you might have multiple pretest measurements. So imagine you have a whole time series. You have a time series, like you have measurements at -2, -1, 0, then the treatment, then 1, 2, 3. And let's just imagine you have an actual model. I mean, maybe it's just like a linear model with a discontinuity or something, or a ramp, or you have some model that you might believe. In that context, if you fit the model Bayesianly, that is basically like controlling for the latent parameters of the time series, or like controlling for the true value of 0 and the true slope at 0. So it struck me that we could frame it that way even if you only have one pretest measurement, and that would kind of break the symmetry. So you're no longer just so the whole idea of subtracting is already, it's like in social science, like naive social science, like, well, I have like different countries different amounts of healthcare spending per person, but they have different GDP. So I'm going to take the ratio, and like taking the ratio is the naive way of like controlling for things, right? Instead, we do matching or regressing or synthetic control or whatever. We want to compare it to comparable cases. So in some way, taking the difference, or even taking the regression, but taking the difference is a very crude idea. And it's just unfortunate that this stupid algebra happens, because it looks unbiased and it makes people think it's so clean. But I'll stop babbling.
Do we have time for one more question? Okay, great. So one question related to that is, so in your chickens example, we kind of sort of suspected ex ante that maybe there was no bias, and then you had a lot of sham data. So you were fairly confident statistically that the bias was close to 0. But I think in a lot of applied contexts, you don't have that much data, and you don't have that much reason ex ante to believe that the sham is 0. States that raise the minimum wage are different from states that don't raise the minimum wage. We might suspect them to be different. We don't have that much data on either of them. And so from a frequentist perspective, like, you're sort of unsure which estimator you should use, then kind of conditioning on which estimator you use as a function of whether you reject the pretest from a frequentist perspective can be kind of problematic. From a Bayesian perspective, of course, like, you can just follow what your prior says or what your posterior says, but if you don't have a lot of data, the posterior may not update the prior very much. And so what your prior is about how much bias there is presumably is going to matter a lot. So I guess I'd be curious to hear your thoughts about how should I think about these trade-offs in a setting where my statistical estimates of how big the sham bias is are not particularly precise.
I've thought about, that's one thing I've thought about. I haven't written about, but I've thought a lot about, especially in preparation for giving this talk. So a couple answers. The first is that at the very least, you can do a kind of robustness study. Like, I can try different values, and I could say, well, what if the biases were this big? Right? The two key parameters are the mean level of bias and the standard deviation of the biases. And so you might have separate views about that right away. So you could try some values. The second thing is that doing the subtraction corresponds to a huge level of the standard deviation of the biases. In fact, even if the standard deviation of the bias, I mean, as you could imagine, if the standard deviation of the bias is the same as the standard deviation of the effect size, then probably the right thing is to subtract 0.5 or something like that. So even if the biases vary a lot and are huge, it's not necessarily clear that, I mean, you could still maybe do better by subtracting 0.5. Another thing is that this analysis gives you a sense that maybe you should be interested in correcting for the mean bias. Now, if you only have, of course, if you only have one study, then there's no mean and standard deviation. There's just a bias, and you don't know it. But then, yeah, I guess the answer, like, if you're in a situation where the estimate is very noisy and you're trying to make decisions based on that, then I kind of retreat to the Bayesian position and say, yeah, I'd like to use whatever prior information I have. It's an interesting thing though, because yeah, it's a little different than the usual Bayes, because the role of the prior is to modulate how seriously you take these data. But then of course I would argue we do that all the time. Like we're always deciding.
But Andrew, we may differ in how seriously we want to take some of these data, and so rather than having you put your prior on there and going with that, I might want to see something where I can then figure out what I would get with my own prior. And so we should see it more as what are we trying to report to the reader so that they can make up their mind, even if they have different priors from yours and mine.
I mean, the prior is part of the model, so people can have all sorts of different models, and a lot is hidden.
Yeah,
I think. I mean, they didn't even report the raw data.
In practice, in these settings, people may have very different views on how likely it is that there is some bias. Maybe not in this case with the sham data, but in other cases, people would have different views on how likely it is they think there's bias, and so they may vary from just subtracting the lagged values versus the regressing things on that.
No, I'm with you on this, but like, let's, okay, I think there's a benefit to having to commit. So like, just for example, suppose the people who did this experiment and they thought ahead of time, well, we're going to do the sham. There could be a large, well, the first thing is they might have not even thought about, they might have just thought you're supposed to do a sham, right? So let's formalize it. Yeah, we're doing a sham because there might be a big bias. And if we don't do the sham, we can get the wrong. How big might the bias be? Well, okay, if the bias is large enough, we really have to do some adjustment. If the bias is small, we're going to be worse off correcting for it. So does that mean we shouldn't do it? No. Well, maybe we should do a little preliminary study. Maybe we just, like if you're measuring something on a scale, you do some measurement of the scale first, right? To check. So maybe we should like do some little experiment and see how big the bias might be if necessary. So recognizing that the size of the bias is important and the correlations of the bias are important can motivate you to try to, sorry, Beth, I'll stop talking now.
Yeah, no, well, this is great. And I'm sure we can continue this discussion for a lot longer. This
yeah, I'm not disagreeing. I've seen a lot of cases where people can have different priors, but the analysis that people do corresponds to a prior that nobody would believe, like, which would be like sigma b equals infinity.
Andy, but I'm confused about the idea of basically doing a pilot to see what the bias is. But if the bias is small but meaningful, the pilot will not be able to detect that very well. It's going to be very insensitive because it's I mean, I would guess the bias to be smaller than the effect, but still meaningful in the effect, in which case I need a lot of data to estimate the bias, don't I?
Well, sure. No, I'm not saying like do a pilot and say the bias is 0.1 and then use 0.1 for forever. What I'm saying is like, think of it as a kind of a science problem, like as a measurement problem. Like I'm doing this, I'm concerned about the bias. Well, doing the sham gives me an estimate of how big the bias is. This gives me information about the bias. I know more about the bias after doing it than before. If it turns out, if you're in a situation where there might not be a lot of bias, and if you do this simple correction, you multiply all your standard errors by square root of 2, and you double your data collection costs, then well, maybe it's worth thinking about like how much you're going to learn about the bias when you do it. I mean, the same thing with the underlying effect size too. When people come up with a certain estimate and then they get a standard error, like, well, what's the population of possible estimates you could see? Like I think committing to it, if someone wants to write a paper and they say, well, we think the biases could vary by this huge amount, so therefore we're doing this subtraction, that's our result, then that's fine. They're saying under these assumptions, this is our best estimate. And then I can say, well, under the assumption there's no bias, this is an estimate. And under the assumption that there's this amount of little bias, here's another estimate. I think that takes one forward. I think that's a good direction to go. It's not so much one's personal belief about the bias, it's more like even committing to a statement about it is already moving forward. But yeah, when I said do the pilot study or whatever, the point was not that would give you the answer. The point was more that they should think of it as a problem that they can gather information about.
Thank you. Sorry, I'm here to stop the party. So we are out of time. Thank you so much. Thank you, Andrew, for a nice talk. I'll stop your share just to wrap up.
Thanks for the opportunity to reach this influential audience of causal inference people.
Of course. Okay, so before we wrap up, just to say thank you again to Andrew and to all our discussants for a lively discussion. So Jonathan, Elizabeth, Avi, Pedro, also Guido for chiming in. Thank you all. Thank you for being here and asking all the questions, the audience. Next week, we'll have a talk by Michael Hudgens and Changhua Li from University of North Carolina at Chapel Hill on efficient non-parametric estimation of stochastic policy effects with clustered interference. Hope to see you all there, and thank you again for coming.
Thanks so much for reading my paper and making comments.